First of all, I also want to express my I want to thank organizers, people from my Ghana's committee. Namely, I want to express my attitude to Professor Karapetyan's Alexei. Thank you very much for invitation, for giving possibility to talk here. Everything okay with hospitality. Thank you very much. My presentation title is Fractional Stochastic Evolution Equations with Balakrishnan's White Noise. This is my joint work with my students, Sukhov Shkorbekov and Jamshed Rakhmatov from Dushanbe, from Academy of Sciences and Tajik State University. And I have a content next, okay, like this. Okay. This is content, introduction, then finitely additive Gauss measure in Hilbert space, then Cauchy problem for fractional differential equation in Hilbert space, first deterministic case, then I talk about Balakrishnan's white noise, then Cauchy problem for fractional differential equation in Hilbert space, the stochastic case in small conclusion. Okay. A difficult problem in the theory of measure in integral is the analysis of it's not so good for me, it's small a little bit, is the analysis of the relationship between finitely additive and countable additive measures. This is an old problem. First publication, first fundamental results on this problem we can find in publication of academician Alexander Danilovich. It is 40s years, 20th century, and also and joint paper Kosaku Yoshida and Hewitt. This is two big specialists in functional analysis. This publication dated by 1950. Second publication. These papers consider real-valued measures that have the property of finite additivity, but not necessarily countable additivity. The current state of the problem is detailed in a very recent publication, this year publication, Daumu and Weiss. This is a very big paper, about 30 pages, and very deep and very strong analysis of this problem of the current state. Yes, and the introduction to the cited work, to this three, it was noted that in contrast to the theorems of Prokhorov and Vitaly Khan-Sachs, in which it was established that under regularity conditions, a sequence of countable additive measure converges to countably additive measure. And we can prove that for every finitely additive probability measure P on a totally bounded separable metric space, there is a sequence of countable additive probability measure Pn such that this kind of limit we have for every bounded uniformly continuous real-valued function phi. Also in this publication, authors stress that on the other hand, in contrast to the portmanteau theorem, it is very fundamental theorem on this theory, portmanteau theorem, Such convergence does not take place for simple bounded continuous functions. Thus means that the assumptions of this theorem, portmanteau theorem, sharp, not so easy. In the case of infinite dimensional phase spaces, in my presentation we talk about Hilbert space, infinite dimensional space. Other mathematical difficulties arises. Balakrishnan, American mathematician, in his monograph name is Applied Functional Analysis, publication 1976. Describes the structure of measurable sets of Hilbert space consistent with its topology. It is important that the theory of measure in a Hilbert space differs from the classical one, and that the measure defined on the algebra of cylindrical sets turns out to be only finitely additive. It is very unusual result, but this is a result of Balakrishnan. Our presentation is devoted to the solvability of stochastic differential equation in Hilbert space with a finitely additive probability measure and with a fractional order of the derivative. We talk about two novelty. First is our Gauss measure is a finitely additive, and also we talk about fractional order of derivative. The second section of our work, we presented a result related to the finitely additive probability measure on Hilbert space. Gaussian measure is constructed to illustrate the singularity of the infinity dimensional case. The concept of stochastic integral based on finitely additive probability measure on abstract space is all discussed and discussed its relationship with the Ito integral is explained. And the third section, study deterministic fractional evolution equation in Hilbert space. The result obtained in publication of two professors from Pisa University, Sforza and Loretti, Italy, for homogeneous equation on the solvability and representation of solution brought to the case of non-homogeneous equation. In this publication, we have no result about non-homogeneous equation, and we try to find a condition for existence and uniqueness of solution of non-homogeneous equations, and both in deterministic case and stochastic case. And the fourth section, the concept of Balakrishnan's white noise is introduced and its properties are studied. I want to say that Balakrishnan white noise, this is a Gaussian white noise with finitely additivity, not with countable additivity. This different. And last section, on the basis of the concept of elementary random variable or physical random variable, these two notation also belong to Balakrishnan. He said about elementary random variable or physical random variable. Because he stressed that physical random variable mostly countably additive. not contemplative. Contemplative is very good idealization. And an application, we can find this kind of stochastic processes. Theorems on the existence and uniqueness of a weak random solution of fractional evolution equation are established. The results obtained a generalization and strengthening of a number of works. I show these works and references and end of my presentation. Also, probabilistic characteristic is found. I means correlation operator corresponding to stochastic solution. I can find this correlation operator. It is very important probabilistic characteristic of stochastic solution. It is well known that the classical measure theory in finite dimensional spaces originated in the works of Henri Lebesgue on the theory of integration and found its application in probability theory, mathematical physics, functional analysis, and other branches of mathematics. In particular, Andrei Kolmogor's interpretation of the probability of an event as a measure of a set significantly influenced the future development of probability theory. Maybe it is not need, I don't know, to, you know about it. The theory of measure and infinite dimensional Hilbert space differs from the classical one, and that a measure defined on the algebra of cylindric sets turns out to be only finitely additive. Balakrishnan gave a canonical example in the form of Gaussian measure illustrating this feature of probability measures on infinite dimensional spaces. Next, my pages, I talk about this issues. I talk about algebra of cylindrical sets. I think it is more or less you know about it. I don't talk about it. Only one lemma. I would like to show one lemma. This lemma, this station is this applied functional analysis of Balakrishnan, monographia. The class of Borel sets B coincides with the smallest sigma algebra of, containing all cylindrical sets. It means that we can prove that intersection of cylindrical sets is also cylindrical set. We can prove that okay, not this, not here. The set theoretic complement of cylindrical sets, cylindrical set, intersection in union of cylindrical sets, also cylindrical sets, two cylindrical sets with bases B1 and H1 and B2 and H2 coincide this if and only if B1 is equal to B2. It is very important properties of cylindrical sets. Next. In subsection 2.2, we talk about Gauss measure, NRN, and Euclidean space. This is a formula for Gaussian measure, standard Gaussian measure, 2-1. We can write this definition, this formula through radon-Nikodym derivative. Next, and more general case, Gaussian measure with a mean mu from or and variation sigma sigma is positive, is given like this. The Gaussian measure with mean mu greater than 0 is called the centered Gaussian measure. I talk about Dirac measure here, standard Gaussian measure on Rn, and then in next subsection 2, 3, we talk about Gauss measure on cylindrical sets and Gilbert space. Okay, and Gilbert space, not Euclidean, but in Gilbert space we take Z cylindrical sets with base B and basis space HM. Then we have a definition to first and two. We can write Gaussian measure of cylindrical set through countable additive probability measure on the sigma algebra of Borel subsets and HM, in particular if ZK, this is not good. This is we talk about disjoint cylindrical sets with common base space and corresponding bases bigger. Then we have a formula like this for countable additivity. Also, we have consistency conditions. In order for the measure mu to be correctly defined, it is necessary that the following condition be satisfied. If Z, this is not small z, it's big Z, Z is equal to B plus HCM, it is like this, where HP subset orthogonal to HM, then we can write for M for measure this formula, and then since M is a countable additive measure on Borel subset of the finite dimensional space HM, it follows that we have a formula like this. I need to say that measure in Gilbert space is this is a multiplication of measure, infinitely multiplication of measure of one dimensional spaces. We now introduce Gaussian measure on Borel sets with a matrix of second moments like this, and here R is given operator. This, commonly it is not bounded operator, it's, maybe it's non-bounded operator. Obviously, this measure does not depend on the chosen basis. Note that the matrix or IG can be degenerate. It is easy to see that the introduced measure satisfies the consistency equation. We denote the cylindrical measure by mu. Next, we talk about one example and Hilbert space of finitely additive measure like this. It is a very long talk, but most important, this proves that there is no counted additive measure on the class of Borel sets B that coincides with the measure mu on cylindrical sets. Indeed, if P is such a counted additive measure, then we have inequality like this, as well as PAN. This is a mu n, and we come to contradiction. And in Gilbert space, we have no Gauss measure with countable additivity. Okay, next section. This is a Cauchy problem for fractional differential equation in Gilbert space. This is also very special issues, because if we have a integer order of derivative, this is a very developed theory, like monography of, for example, Selim-Grigorich-Crane, and etc. We have many monography in this case. But if we have a fractional order of derivatives, we have no sources like Crane's books. Okay, we have many publications, many papers, but it is a little bit difficult. We meet with very serious mathematical difficulties, and we need special talk about it. Our goal in this section is to define a weak solution to a class of fractional abstract differential equation. In this case, the fractional derivatives, and the equation will be Caputo derivatives. We have many kind of fractional derivatives. Here we talk only about Caputo derivatives. Results will be established for weak and strong solution of homogeneous and non-homogeneous equations. This is also preparation. It's operators in fractional Sobolev vector space. I want to explain one results. This is theorem 3.1. H be let H be a separable Hilbert space. Then Riemann-Liouville operator like this from L2 to L2, beta between 0 and 1 is injective, and its range, or IB beta, is determined by this formula. And second result for the Riemann-Liouville operator, I beta, and the inverse operator, I minus beta, the equivalency of following norms are true. We need this results in future for our theorem of existency and uniqueness. In this section through 3.2, we talk about fractional derivatives in Mittag-Lefleur functions. I think you know about this is a Caputo derivative of order alpha between 1 and 2, and then several properties of this kind of derivatives, and this function through series E alpha beta z is equal to this series k from 0 to infinity zk. Gamma, it is a Euler function. Also, we talk about properties of this function. We introduce Laplace transform of function phi, and also Laplace transform of Mittag-Lefleur functions. This lemmas 2, 3, 4, 5, 6 about this kind of properties. Next, we talk about weak solutions of homogeneous fractional equation. This result belongs to this professors from Italy, and he gave a definition of weak solution, very special, like this. This is a evolutionary equation. A is the operator. A is the operator non-bounded operation, because we talk about generalization of partial differential equations. This kind of condition 318 need for definition of weak solutions. Remark about this solution. This is lemma, and we have a theorem 3.10. If u0 belong to domain of square A operator, and u1 belong to Gilbert space, then the function 3.20 is the only weak solution satisfying this initial conditions. We have a scheme of this proof of these theorems. Okay, I want to explain our result and non-homogeneous equation. This is new results. It is not from. It is our result. We give equation like this, and then we can find representation of equation of solution of this equation. Here, E alpha, E alpha 1 and E alpha 2. These are Mittag-Lefleur functions. We have a theorem 3.12. This is a weak solution of equation. I need weak solution because in next section we talk about stochastic equation. In stochastic equation, if we have a permutation or stochastic random permutation, we need to talk about weak solution. We have no strong solution in this case. This theorem 3.2 about exactity and uniqueness of weak solution with for equation with initial condition. I show this. Okay. Now, and section 4, I talk about Balakrishnin's white noise. Okay, Balakrishnin white noise. We can say that this is white noise, Gaussian white noise with finitely additivity. With finitely, there's no countable additivity. We talk here about this triple probability trip, very special. Space of events is Hilbert space. B is not counted by algebra. It is only algebra. B is only algebra, and measure here is countable additive measure. In this special case, we can talk about Balakrishnan white noise. We need finite additive measures on algebras, since in this case we can consider Gaussian random variables with non-nuclear correlation matrices. Here I need to talk about operators. In the Balakrishnan monograph 7, developing the scheme of Danforth-Schwarz, a new approach to definition of random variable is proposed. I talk about this. We have an abstract space, we have a C algebra of subset. This is the algebra of cylindrical sets, only cylindrical sets, and mu finitely additive probability measure defined on C. We need a new definition for random variable. Function f omega, mapping omega into a Hilbert space is called a random variable in the weak sense if for any finite sets of elements phi I from the Hilbert space conditions, we meet two properties here. The set omega, f omega, this is a scalar product, belong to B, where B is Borel set in Euclidean space, belongs to C. The measure induced on Borel sets is quantum additive for every n. Then we can define ordinary random variable. We talk about physical random variable, and in this subsection we deal with the properties of this new kind of random variables. Okay. Next, we give extension of physical. This is F, physical random variable. Definition: F from H to H be H measurable Borel map, and let Pn be a sequence of finite dimensional projections strongly convergent to the identity operator. The mapping F is called physical random variable if we have these properties. Condition 2 is equivalent to the fact that there is a limit, this limit, independent of Pn, of projection, finite dimensional projection. F is a physical variable, stochastic variable, then mu can always be extended to events of the form of the f minus 1b, where b prime is a Borel set in H prime, using the equality like this. To complete our construction, we introduce the Balakrishnan noise model. It is natural to assume that the Gaussian noise has a much larger bandwidth than just the switch. Okay.
5 minutes.
Okay. Okay. Thank you very much. Thank you. Such a mapping is called Balakrishnan white noise. Okay. This is a definition about FCV. We have a TOTHA theorem 4.4.5 about necessary criteria for FSF, and in the end I have an equation 5.1. This is a fractional differential equation with stochastic perturbation BWV omega t. A is non-bounded, but B is bounded operator. This kind of perturbation, we talk about additive perturbation. We need a condition like 5.2, and we have a result about weak solution, unique weak solution of this problem. 5.1, this problem, 5.1 and 5.2. Then we talk about correlation operator corresponding to the process ut omega. The process ut omega is defined at each time t, assuming as u0 and u1 are given, we get a formula for correlation operator. In conclusion, I would talk about application of this kind of Gaussian finitely additive white noise, but all Balakrishna's white noise as a uniform power spectral density, is normally distributed, sums with the useful signal, and is statistically independent of signal. Such measures are used in the digital signal processing and space communication systems, and the analysis of the probability of securities. Thank you very much. This is references here. Thank you very much. Thank you.